Imagine a robotic arm reaching for a coffee cup. It misses the handle, hesitates in midair for like 5 seconds, and then pulls back to try again.
Right.
Any human watching knows instantly that the robot just failed and is resetting. But today's state-of-the-art AI value models, they look at those frames and actually think the robot is making great progress.
Yeah, it's a huge blind spot.
Welcome to AI Paper Slop, the YouTube series where we summarize the latest AI and tech papers so you don't have to. Today we are looking at a paper that completely fixes this blindness. It's called World Value Models for Robotic Manipulation, published in June 2026 by researchers from ByteDance Seed, Peking University, and Tsinghua University.
It's honestly a massive shift in how we handle robotic training.
So here is the 60-second summary for you. If you are building a generalist robotic value model right now, you are almost certainly using a vision language model, and VLM as your backbone.
Almost definitely.
Right. But VLMs are terrible at temporal reasoning because they are trained on static images. They don't natively understand time or velocity or physics.
Not at all.
So this paper flips the script by using a video world model, instead specifically 1.2.2. The authors built a dual-stream diffusion transformer using flow matching, and that creates a world value model, or WVM.
And because it's built on a massive video generation model, it inherently understands physics, history, and, future planning.
Exactly. And to prove it works, they had to invent an entirely new 800 trajectory benchmark just to test how well models detect robot hesitation and retries. The result is a state-of-the-art model that drastically improves downstream policy learning.
We're finally moving away from models that just look at what a robot is holding in a single frozen frame, We're moving toward models that inherently understand the physical continuum of what the robot is attempting to do over time.
Let's ground this for the ML engineers tuning in. Why do we even care about value models in the first place? I mean, we are currently in the era of massive behavioral cloning. The prevailing wisdom just seems to be scrape 100,000 hours of teleoperated robot data, throw it out of policy, and let the neural network sort it out.
I mean, you can certainly try to throw raw, unfiltered data sets at a policy, but real-world robotic data is incredibly messy.
Yeah.
It is full of humans making mistakes, dropping objects, or just pausing to scratch their nose while holding the controller.
Oh, totally.
If you feed that directly into a behavioral cloning pipeline, your policy learns to replicate those mistakes. It learns to hesitate. So to prevent that, you really need a reliable critic.
A filter.
Exactly. You need an automated way to scan a trajectory and output a learning signal that basically says, this sequence of frames is actually making progress toward the goal, or this sequence is a total failure. That offline data filter is your value model.
Because relying on human annotation at that scale is just impossible. You can't pay researchers to sit and watch 100,000 hours of video manually labeling every single frame as a good or bad grasp.
Oh, you'd burn through your entire research budget in a week.
Right.
But automated value models have historically struggled with 3 pretty severe bottlenecks. The first is a reliance on simple scalar value supervision.
Okay, scalar value.
Yeah, you feed in a high-dimensional video observation, and the model just collapses all that rich data into a single number.
Wow.
It's a highly sample-inefficient way to train, and it becomes very brittle when you try to scale it up to complex tasks.
It's like grading a massive, complex essay with just a thumbs up or thumbs down.
Exactly.
The student has no idea which specific paragraph was actually good. So what's the second bottleneck?
Well, the models that do actually manage to work around that first issue, they tend to be really over-customized.
Okay.
They are tightly engineered to evaluate a single specific task, like inserting a peg into a hole. The moment you ask that same model to evaluate a robot folding a shirt, it completely collapses. It has zero generalist capabilities.
Which brings us to the third and honestly most critical flaw, the backbone itself.
Right. Generalist models today are built on VLMs. And VLMs inherit internal representations that were optimized for static images.
Right, because that's what they're trained on.
At best, they are optimized for temporally sparse visual observations. So maybe looking at a frame from the beginning of a video, one from the middle, and one from the end.
So using a VLM to judge a robot's temporal progress is, it's like trying to review a movie by looking at 3 random screenshots.
Exactly.
You might be able to tell me who the actors are or what the lighting looks like, but you completely miss the plot. You can't tell me the velocity of a car or if it narrowly avoided a crash because you just don't have the frames in between.
It's honestly even worse than just missing the plot. It's like trying to predict the next scene from those 3 screenshots.
Oh, man.
Accurate value estimation mathematically requires a deep temporal understanding. You have to ground the robot's current state using its historical context and simultaneously plan over its future outcomes. But a VLM just sees a picture of a robotic gripper floating near an apple.
And it assumes, hey, gripper near apple, task complete.
Right. But a world model naturally excels at modeling dense temporal dynamics. It forecasts future states. Because it was pre-trained on massive video generation tasks, it already understands the spatial and temporal physics of the real world.
The spatial temporal prior is already baked into the weights. Like, the world model already knows that if a gripper closes on thin air, the apple isn't going to magically float into its grasp. Gravity exists. Friction exists.
Yeah, exactly. And world models have achieved incredible success in video generation recently, which is why the authors used the 1.2.2 model here. It intrinsically possesses that dual property historical context and future forecasting, which is exactly what a generalist value estimator needs.
Theoretically, a world model sounds like the perfect critic. But let's talk about the actual engineering.
Sure.
How do you physically take a 5 billion parameter video generation model and just bolt a value estimator onto it?
The architecture is genuinely clever. They utilize the video VAE, the variational autoencoder, and the video diffusion transformer, or DIT, from 1.2.2. When they process a chunk of video, they structure the input very specifically. For a value chunk anchored at a specific time window, they feed the VAE a clean video clip consisting of one prefix frame plus H current observation frames plus H target future frames.
Wait, so H is just the horizon length, right?
Yeah, exactly.
It looks at the immediate past, the continuous present action, and the immediate future all at once.
Yeah. And the VAE compresses this pixel data into temporal latents. They discard the prefix latent, keep the current latent as context, and corrupt the future latent with noise to use for the video generation denoising process.
Got it.
Then the massive 5.0 billion parameter video DIT processes all of this latent information to deeply understand the scene's dynamics.
But the video DIT's only job is to generate video. It's really just predicting pixels. Where does the actual value estimate, like the progress metric, where does that come from?
So they introduced a parallel lightweight value stream. It is a 0.7 billion parameter value DIT. It mirrors the architecture of the video DIT, just scaled down substantially. And this value DIT is tasked with predicting the value chunk from noisy value tokens.
Hold on, let me stop you there. If you have a value stream that needs to pull physics information from the video stream, they have to talk to each other.
Right.
And if you have a value stream attending to a video stream during training, updating gradients based on some arbitrary progress metric, doesn't that bleed over and corrupt the video model's internal representations? You're basically forcing a pristine physics engine to suddenly care about a human-defined task reward.
That is the exact trap they had to avoid. If the video stream starts altering its weights to optimize for a specific robotic task value, it loses its generalized understanding of physics. It just becomes biased.
Yeah.
To solve this, they implemented a mixture of transformers, or OT architecture. The crucial mechanism here is an asymmetric attention mask.
Asymmetric attention mask. Break that down for me.
During the multimodal self-attention layers, the system controls which tokens can basically see each other. The value tokens are allowed to selectively attend to the structural video latents.
Okay.
They can query the video stream to gather all that rich temporal and physical context, but the attention mask blocks the reverse path. The video tokens are strictly masked, so they cannot attend to the value tokens.
Well, I love that. It's like a one-way mirror in a police interrogation room.
Exactly.
The value DIT gets to sit in the dark room and observe the physics engine doing its thing, extracting whatever context it needs. But the video model has no idea the value model is even there. It just keeps generating video.
That one-way flow is the secret. It minimizes representation interference with the video generation stream during backpropagation. It preserves the backbone's intrinsic video modeling capacity while allowing the value stream to successfully derive robust predictions from its latent temporal features.
The architecture makes total sense. You have this parasitic, in a good way, value DIT watching a massive video DIT through a one-way mirror. But earlier we talked about how standard scalar regression is incredibly inefficient for training. If outputting a single number is too sparse a signal, what is this value DIT actually outputting?
Instead of outputting a single scalar value for the whole sequence, WVM predicts a distributional value chunk.
Okay, what does that mean?
For an H-frame observation sequence, it outputs a length sequence of per-frame values. But they didn't just stop there. They completely abandoned traditional scalar supervision and standard categorical bins.
When you say categorical bins, you're talking about things like the H.L. Gaussian heads, right? Where you divide the concept of progress into, say, 50 discrete buckets and just run classification to see which bucket the current frame belongs to.
Yeah, that's the standard approach.
Yeah.
The problem with categorical heads is that their fixed, pre-specified bins preserve the conditional mean but completely discard fine-grained density variations.
All right.
Think of it like a staircase. If a robot makes a microscopic progression, maybe it moves its gripper 1 millimeter closer to the cup, it might not be enough to bump it up to the next step on the staircase. So the model registers zero progress. It learns nothing from that frame.
So what do they use instead of a staircase?
A continuous ramp, mathematically speaking. They use flow matching.
Flow matching.
Flow matching is a generative modeling technique often used in image generation to map noise to a complex data distribution. But here, they apply it to value prediction. They train a velocity predictor to map a simple noise distribution to the target value distribution.
How does that actually solve the staircase problem?
Because flow matching provides a continuous return density without bounding the support or resolution. It retains those highly fine-grained local value differentials.
Ah, I see.
You need that microscopic sensitivity to rank temporally adjacent chunks to know with certainty if frame 10 is actually better than frame 9, even if the visual difference is just a few pixels of movement.
The continuous gradient makes total sense. But wait, let's think about the data they are actually training this on.
Sure.
If they are training this on a data set of expert demonstrations like the massive OpenX embodiment data set, the progress is always monotonic.
Yes.
The human teleoperator always successfully picks up the apple. The progress curve is always a straight line up from 0 to 1. How can the model possibly learn to recognize when a robot fails or hesitates or drops something if it has never seen a failure in the training data?
It is a classic problem in offline reinforcement learning.
Yep.
If the model only ever sees success, it assumes everything is a success. It suffers from massive out-of-distribution failure when deployed.
Right.
So to counter this, the researchers used two incredibly clever data augmentations. The first is video rewinding.
Wait, like literally playing the video backwards?
Basically, yeah.
Doesn't that completely break the world model's physics prior?
Yeah.
If you drop an apple and reverse the video, it looks like an apple defying gravity and flying up into a gripper.
You would think it would break the physics engine. But remember, they are doing this at a specific chunk level, and they are manipulating it to simulate specific suboptimal behaviors.
Okay.
They take an expert trajectory window and artificially manipulate the frames. Sometimes they preserve the frames normally. Sometimes they take a single frame and repeat it multiple times to fake a plateau in progress. This simulates a robot hesitating or stalling.
Okay, freezing a frame makes sense for hesitation, but what about the rewinding?
They take a successful monotonic segment where the robot approaches an object, and they literally reverse the order of those specific frames, relabeling the target value to decrease.
Oh.
Because it's an arm moving back along a path it just took, it physically simulates a robot attempting a grasp, failing, and retracting its arm.
Ah, I see. Since it's just the arm retracting, it doesn't look like a physics violation like defying gravity. It just looks like the robot gave up and went backwards.
Yeah.
So you take a perfect success, hit rewind on that chunk, and tell the model, hey, the value is dropping here. This is what a retry looks like. It exposes the value stream to negative progress profiles it would otherwise never see.
The second trick is prefix randomization. Remember how the model takes in a prefix frame to help establish inter-chunk continuity during inference?
Right, because you can't process a 5-minute video all at once. You process it in overlapping chunks, and that prefix frame anchors the current chunk to the previous one.
Yeah, but the danger with that architecture is causal shortcuts. Neural networks are inherently lazy. They will always find the easiest way to minimize a loss function.
Oh, totally.
The value model might look at the value of the prefix frame and just linearly extrapolate the next few values without actually bothering to analyze the complex visual evidence in the edge current and future frames.
It just cheats off the first frame.
Exactly. So analogous to classifier-free guidance dropout used in text-to-image models where you randomly drop the text prompt to force the model to learn the image, unconditionally they randomize the prefix value here.
Oh, that's smart.
50% of the time during training, they replace the true prefix value with a random scalar between 0 and 1. By feeding it garbage for the prefix, they force the valued AIT to actually analyze the visual evidence in the current frames to figure out the real progress.
So through flow matching for fine-grained resolution, video rewinding to teach it what failure looks like, and prefix randomization to stop it from cheating, they've trained this model to accurately track progress.
Right.
But here's my next question. If this model is uniquely trained to recognize failures and plateaus, how do you evaluate it? Because the standard metrics we use in the community are designed for success data.
You've hit on the exact reason they had to introduce a new benchmark. The standard way the community evaluates value models is using something called value order correlation, or VOC.
VOC, this basically measures if the predicted value goes up when the ground truth goes up.
Yeah, it uses Pearson correlation to measure the linear relationship between the predicted progress and the true progress. But there is a massive mathematical flaw with VOC when you try to apply it to real-world suboptimal robot behavior.
Which is?
Think about the math of a Pearson correlation. It measures how two variables change together. But if a robot hesitates, if the arm just stalls above a tray for 5 seconds doing nothing, the ground truth task progress is invariant. It's a flat line.
Oh, the variance is 0.
Yeah.
And the Pearson formula divides by the standard deviation, so you end up dividing by 0.
Exactly. The metric becomes mathematically undefined. VOC only works on perfect, monotonically increasing expert trajectories where the value is constantly changing.
Wow.
But to properly test WVM on messy real-world data, the authors had to curate Suboptimal-Value-Bench.
Let's look at this benchmark, because the sheer amount of manual labor involved to fix this mathematical flaw sounds intense.
It was. They curated 800 trajectories across 3 different physical embodiments, an Agilex dual-arm robot, an ARX single-arm, and a RoboSuite simulated arm. This spanned 15 different manipulation tasks. And they didn't just collect the data. They had human annotators manually label the frame-level ground truth task progress, focusing specifically on 2 suboptimal modes, hesitation and retry.
So they finally have a ground truth for what failure actually looks like on a frame-by-frame basis. What are the actual metrics they replace VOC with?
They introduced 2 new metrics. The first is hesitation RMSE. This measures prediction drift when a robot stalls.
Okay.
If the robot is hovering above a tray, the true value is constant. A perfect model outputs a flat line and gets a root mean squared error of 0. A bad model will hallucinate progress, or its predictions will wildly fluctuate, resulting in a high RMSE.
Okay, so hesitation RMSE catches the robot when it freezes, but what happens if the robot actually makes a mistake and has to pull its arm back? Does that require a completely different way of measuring?
Yeah, that requires retry VOC. This measures how well the model tracks a downward trend. If a robot misses a grasp and retracts its arm, the true progress drops. Retry VOC isolates those specific retracting temporal windows and calculates the correlation. A perfect model tracks the downward trend and scores a +1. A model that is temporally blind and thinks the retracting arm is still making progress towards the goal will score a -1.
The setup is rigorous. We have the architecture, the continuous training, the new metrics. If I'm building a robotics pipeline today and I'm looking at my compute budget, do I switch to WVM? Let's look at the numbers. Does this highly engineered system actually beat the baselines?
The numbers are definitive. WVM crushes the competition.
Nice.
They tested it against 6 competitive baselines, including GVL, VLAC, and Robometer. On the suboptimal value bench, WVM achieved an average hesitation RMSE of 0.05. The next closest baselines, GVL and Robometer, were way behind at 0.14.
So WVM is nearly 3 times more stable when the robot stalls. It doesn't hallucinate progress just because time is passing.
Exactly. And on retry VOC, where it has to detect a failed grasp and a drop in progress, WVM scored an average of 0.78. The best baseline could only manage 0.60. And many of the VLM-based baselines actually scored in the negative, meaning when the robot was failing and retracting, the VLM thought it was succeeding.
That brings us right back to the VLM problem we talked about at the beginning. If you only look at static frames, an arm moving away from a block looks visually identical to an arm moving toward a block. Without the historical vector and temporal context, you are just blind.
And just to prove it wasn't sacrificing performance on normal tasks to achieve this, WVM also hit an average expert VOC of 0.95 on clean, successful trajectories, outperforming all baselines there as well.
I am curious about the compute costs, though. Running a 5 billion parameter video DIT alongside a value stream sounds, well, heavy. Could you just use this architecture but completely freeze the video weights to save compute? Like, put a value head on it but don't let it co-train?
They ran that exact ablation.
Yeah.
If you freeze the video weights, meaning the value stream cannot rely on a continuously co-trained world model prior, the performance falls off a cliff.
Really?
Yeah, the retry VOC drops to an abysmal 0.45. It proves that explicit video code training is absolutely indispensable. You can't just slap a value head onto a frozen static model and expect it to understand the nuances of physical failure. The continuous flow of temporal dynamics being updated together is the secret sauce.
Let's connect this back to the ML engineer listening right now. You've got this amazing world value model. It understands physics. It tracks hesitation. It scores a 0.78 on retries VOC. What do you actually do with it? How does this translate to a robot successfully making my morning coffee?
It translates directly into your policy learning pipeline. As an engineer, you use WVM to filter your noisy, mixed-quality behavioral cloning data before you ever start training your policy.
Okay.
The authors prove this by using WVM's chunk-level advantage proxy to filter BC data.
How does that filtering actually work in practice?
Well, they tested two methods. The first is advantage-weighted regression, or AWR. In AWR, you mathematically weight the training loss of your policy based on how much WVM says the action improved the task progress. If WVM says an action was a huge step forward, the policy gets a strong update. If WVM says the robot hesitated, that frame gets a tiny weight, so the policy effectively ignores it.
That makes sense.
The second method was even simpler. Just use WVM to rank all your data chunks, throw away the bottom 30%, and train vanilla behavioral cloning on the top 70%.
What was the impact on the final success rate of the robot?
In simulated bimanual tasks using RoboSuite, and more importantly, in real-world bimanual tasks using the AgileX robot, the success rates improved drastically over vanilla behavioral cloning.
Wow.
Because the policy was no longer being forced to learn from hesitations and retries hidden in the dataset, it learned the optimal path much faster and much more reliably.
To summarize the massive paradigm shift we've explored today in this deep dive into the source material, we are witnessing the end of static VLM evaluators. We are moving to dynamic, physics-aware world models for robotic value estimation. And crucially, we're moving away from only evaluating models on monotonic expert data toward rigorously testing on suboptimal behaviors with benchmarks like Suboptimal-Value-Bench.
It is a complete maturation of how we handle robotic data. We are finally treating time as a core dimension of the problem.
If you are out there training robotic policies, this matters to your daily work because the quality of your data filter dictates your ceiling. You can have the greatest policy architecture in the world, but if you feed it garbage, it will output garbage.
Yeah, exactly.
WVM offers a plug-and-play way to salvage massive amounts of noisy, real-world data that you previously would have had to throw away or manually label.
But before we wrap up, I want to offer a final lingering thought for you to think about.
Okay.
We've just seen that video world models natively possess the spatiotemporal priors necessary to judge physical progress better than anything else. They understand the physics of the physical world. But what if we zoom out from robotics?
Where are you going with this?
Well, think about it. If a world model can inherently act as like a perfect critic for physical tasks by understanding states over time,
Yeah.
could we eventually train software-based world models to act as intrinsic critics for purely cognitive reasoning tasks over time?
Oh, wow.
Right? If a model understands the physics of logic, could it evaluate the progress of an LLM's chain of thought, just like WVM evaluates a robot arm reaching for a cup?
Yeah.
Could it detect cognitive hesitation or logical retry mid-generation?
A world model for pure logic. If you can map the trajectory of a thought the way 1.2.2 maps the trajectory of an arm, the implications for reasoning models are staggering. Thank you for joining us for this deep dive on AI paper slop. Keep iterating, keep exploring, and we will catch you next time.